Hello. Okay, so now that you know a little bit more about chemical reactions, a way to classify them and those kinds of things, there's one more type of reaction that I want to talk about today called a reversible reaction. This idea takes into account that sometimes your reactants don't just stay reactants and your products don't just stay products. For example, we're going to be talking about the fact that you can have reactants that go back and forth between reactants and products. So sometimes the reactants act like reactants and go towards the products, but sometimes the products act like reactants and go back to the reactants, and it just goes back and forth. That's called a reversible reaction, and I have a really quick little video to just sort of represent that. This is sometimes known as the traffic light demo. You'll see that really fast why that is. So a reversible reaction is one where the reactants go to products, but then the products can sort of break down and go back to the reactants. So what's happening here is you see this yellow substance, you see someone shake it up, which makes some oxygen go in. That makes it turn red. And then more oxygen goes in, that makes it turn green because of the chemicals that are in there. But as it sits here for a little while, what you'll start to notice is, well, that oxygen is no longer as mixed in as it used to be. And you can see that the color is starting to change a little bit. So as it goes back out, it turns similar to the, let me back that up just a little bit. You'll see that it turns back to that kind of red color, and if it stayed in there long enough, if it sat there long enough, you would see it turn back into sort of that yellow color too. So that idea is this reversible idea. So where it goes from the yellow to the red to the green, and then back to the red, and then if it sat long enough, it would go back to the yellow as well. So that's this idea of a reversible reaction, and that's another type of reaction that's possible. So reactants into products, products into reactants, and what happens is there's this thing called Le Chatelier's principle that says that when that happens perfectly, where the reactants going into products and the products going into reactants, when that happens at the same amount of time, that's something known as dynamic equilibrium, which is what reactants are, or what reactions are trying to do. They're trying to reach this idea of dynamic equilibrium because that is the lowest possible energy state. And one thing that hopefully you just start to keep noticing is that nature is like that. Nature tries to be at the lowest energy, the lowest stress possible. Just kind of like people, you know, we would prefer to be low stress. So like when we get stressed out, we do something to relieve that stress. If you think of like, maybe you talk with friends, or you go for a run, or you listen to music, or you drink some tea, or eat ice cream, or whatever it is, like that, people do that. People try to relieve stress in different ways. Well, Le Chatelier's principle is that same idea, only for chemical reactions. So what it does is it says that if a stress is applied to a system that is already in dynamic equilibrium, meaning the reactants and products are going back and forth perfectly, the system, and system just means wherever the reaction is happening. It could be in the body, or in a living cell, or in a beaker, or in a test tube, or in a machine. Whatever the system is, it's going to shift to relieve that stress and return to equilibrium. So again, equilibrium is this idea where it's perfectly balanced. Neither one side is more than the other. It's going back and forth equally. That's dynamic equilibrium. And so that's what we're going to focus on today. So there's three different kinds of stress that a chemical system can go through. And so the first one we're going to talk about is we're going to talk about, well, what if we just change the concentration of the chemicals? So if we have more of the chemicals we started with or less of the chemicals we start with, that makes it hard for that reversible reaction to stay balanced. And again, we're talking about the back and forth reaction between reactants and products. So if we add a reactant, what's going to happen is that's going to push this reaction towards the direction of the products. And let me show you what I mean by that in just a moment here. So think of it this way. If this is trying to stay balanced, maybe like a teeter-totter, or like one of those old-fashioned balances that goes like back and forth, like two pans that, you know, balance back and forth. What this is saying is that you've got too much reactant, so it needs to shift over to the product side, and I need more product then in order to balance it out. That's what this is saying. Well, what if I remove a reactant? So what if there's not enough reactant? Well, then that means there's too much on this side. So if I want to go back to balance, think of this side being too heavy, I need more of the reactant. So if I take away reactant, I need to make more reactant in order for it to go back to being balanced. So if I take away reactant, there's not enough of this, that means there's too much of this, so it shifts back to this side to get back to balance. That's the kind of idea here. It's always a back and forth. It does what it needs to return to being equilibrium. Another thing we could do is, well, what if there's too much product? Well, if there's too much product, that's kind of like the previous one. This side is too heavy. It has to shift back to this side, so back to the reactant side to get back to equilibrium. So always about that back and forth. That's the idea of Le Chatelier's principle. And then one more option is, well, what if I take away a product? Well, if there's not enough product, that means the reactants are going to step it up and make more product to get back to being balanced. So it shifts to the direction of the product. And like it says here, that's a good trick that we can use in our chemistry lab. Because if I'm trying to make a product, if that's the purpose of my job or my factory is to make something, if I take it away as it's being made, then the reactant makes more. If I take it away, the reactant makes more. If I take it away, it just keeps going like that. Now, eventually you could stress out the system so much that it can't get back to equilibrium on its own, and at that point the reaction would just stop. So those rules still apply. It's not like it's a magic thing. It's just a chemistry thing. It will keep itself balanced as long as it can, and eventually if it can't keep back to being balanced, then the reaction would just stop. So that's one option, is changing the concentration of the chemicals that are being used. Well, another option is that I can also do some changes in temperature, because there are some reactions that are very sensitive to temperature. And we're still talking about the back and forth between reactants and products, but this time what we're talking about is that heat could also be a reactant or a product. And so basically what happens is, if I increase the temperature, which would be one option, the reaction is going to shift to whichever side is not hot, right? So it's going to shift to the direction that can absorb some of that extra heat and get it back to being at the normal temperature. For example, think of this one. So imagine, so these are my reactants, these are my products, this side is already hot. So if I increase the temperature, this side that's already hot is now even hotter than it was before. So there's too much heat. So it shifts back to the reactant side to cool itself down and get it back to being balanced. So that's the idea. Just think of it as reactant or product. Whichever side there's too much of, it goes away from that. Whichever side there's not enough of, it shifts towards that. So for example, in this one, if I were to cool the whole thing down, that means there's not enough heat, right? So cooling it down means not enough heat. So it would shift back to this side then, shift to the reactants in order to heat itself up. So you just think of it as a back and forth. So the rule is always whichever side there's not enough of, that's the side I need more of to get back to being balanced. So if it's too hot, that means that it goes away from the side. It wants to cool itself down. If it's not hot enough, then it goes towards the heat side to get itself back to being balanced. So temperature is something that can sometimes affect the equilibrium, all right? The third thing that I want to talk about is, well, what about if we're talking about changes in pressure? That's the third stressor that can happen. And still we're talking about reactants and products. The only thing that's different though is that maybe you remember from other places that really pressure only matters when we're talking about gases. That's the only state of matter that really is affected by gases. And even more specifically, it's only going to affect the equilibrium if you have an unequal number of moles of gases between your reactants and your products. And remember, to get the number of moles, really you're just looking at the coefficients. So we'll just count them. So for example, this is a gas and this is a gas. This coefficient is 2, this coefficient is 1, meaning that this side then has more moles of gases than this side does. So it is unequal. So that means that right now, this side has a lot more pressure already just because there's more moles of gases than this side. So then that means if I increase the pressure of this whole thing, this side is going to have way too much pressure then, so it's going to shift to the side where there's not enough. And so the reactant would go towards the product, shift towards the product to try to relieve that stress. All right, what about this one? This is a solid, so right now this doesn't really notice much pressure. So this side is the side that notices the pressure. 1 plus 1, this has 2 moles of gases on the product side. So if I increase the pressure of this whole thing, this side is going to notice that it's got way too much pressure. So it's going to shift back to the reactant side. So I need more reactants to try to balance out that extra pressure because this side doesn't have as much pressure. And then here's another one. I've got gases for all of them. This has 1 plus 1, so this is 2 gases on this side. 2 gases on this side. So right now, they really have the same moles of gases, so the pressure between both sides is pretty much equal. So if I were to increase the pressure of the whole system, really nothing would change. It would be able to stay at equilibrium because neither side is affected by that change in pressure since it already has the same amount of pressure. So that idea between pressure and temperature and products, really just thinking about whichever side there's not enough of, that's the side the reaction is going to shift to get back to equilibrium. All right, so I'm going to eventually have you do a lab that sort of demonstrates this idea. However, before I do that, I'd like you to do a little practice on your own. And before I have you do a little practice on your own, I'd like to do a little bit of practice with you. So here's how this works to practice Le Chatelier's principle. So what we're going to do is we've got a chemical system. So in this case, we've got hydrogen and oxygen and water. Those are the things that I'm dealing with. That's my chemical reaction. And notice that this is a product which also has heat, and then both of these are my reactants. So if we take this chemical system, which is the whole reaction, and we heat it up, the idea here is that this whole thing is going to get hotter. But this side is already way too hot then because it already had heat. Now it has extra heat, so this side is stressed out. There's too much of it. So what does it do? It shifts towards this side to relieve that stress and cool itself down basically, which means that both of these, that means I need more of them. So we're going to do up arrows in those boxes underneath the reactants. But the only way these two things can increase is if my product decreases, which means there will be less heat because I made more of stuff on this side. So it goes back and forth between reactants and products. It always shifts towards the direction I need more of, away from the thing I have too much of. All right, what about pressure? So here's my system. They're all gases, but let's take a look. 2 plus 1, this has 3 moles of gases. This only has 2 moles of gas. So right now, this side has more pressure to start with. So if I increase pressure of this whole system, this side, there's way too much pressure now. So it needs to shift over to this side so that it can relieve that stress, which means that the product side is going to increase, but that can only happen if the reactant side decreases. So basically it's opposite, right? So to get itself balanced, whatever happens to one side, the opposite happens to the other. So there's your example of increasing pressure. The next one, well, what if we take this system and we add in some oxygen? Well, oxygen is on the reactant side. So if I add in oxygen, that means there's too much oxygen, which means this side is stressed out. There's too much of it. So to relieve that stress to get back to being balanced, it goes towards the product side. So the products needs to increase, but that can only happen if both of the reactants decrease. That is Le Chatelier's principle. If I stress out the system in some way, what does the system do to relieve that stress and go back to equilibrium? And basically it's always, it shifts away from the side there's too much of, it shifts towards the side that I need more of. So in this case, I added heat, which means I needed less heat, so it goes towards this side. In this case, I added pressure, so I go to this side, which has less pressure. In this case, I added oxygen, so I go away from that side, the side that needs more or the side that doesn't have oxygens to relieve that stress. That is the idea about Le Chatelier's principle. So now you can practice that, and eventually, like I said, you'll do the lab practice that demonstrates Le Chatelier's principle also. Thanks for listening.